So now we're looking at a muscle and how a nerve impulse, or how your body essentially tells your muscle to contract. So how a nerve impulse is sent from your brain all the way down the nerves to your muscle and causes the actual contraction. Because everything in the body happens through electricity and action potentials. Nothing can be done without action potentials. And of course, ATP, what causes the contraction. So like ATP is one thing required, but you also need action potentials. And first, we'll cover action potentials. And for this one, I've gotten a lot better at drawing, so I drew this little guy. And this is a very simplified diagram of what, like, this is a muscle cell, this. This is what a muscle looks like. These are the Z discs and the sarcomeres that I was failing at drawing, but this is a muscle fiber. And now this is a nerve or a motor neuron. A motor neuron is one nerve, and then it's split into different axons or motor neurons that cover individual muscle fibers. So a motor neuron is one nerve that covers many, many fibers. This is only one fiber. And now how it happens is, say you want to contract your bicep or move your foot or do something. So what happens is your brain sends an action potential down certain nerves, and these nerves, which connect to the muscle, but the nerve, what happens is it sends an action potential. I'm not really going to go into the process of how an action potential is created, but it sends an action potential going down the nerve, and then when it gets to the very end of the motor neuron plate, it gets to the bottom, and what happens is this thing, this little axon terminal, it's called the axon terminal on the very end. As you see, it's right here, connecting to the very end of the muscle, or the surface of the muscle. And what happens is when the action potential gets there, it releases something called neurotransmitter, which this neurotransmitter is acetylcholine. Whenever you think of muscles or anything, your body always uses acetylcholine. Acetylcholine gets released from here, crosses this little space called the synapse, synapse is essentially a space between the nerves and the muscle. That's all it is. And then at least these vesicles, which are these guys, and these guys like contain acetylcholine inside of it. And this vesicle, which are right here, goes to the muscle, and you have all this acetylcholine getting to the muscle, or getting to the surface of the muscle. And when this happens, the acetylcholine causes another action potential to happen on the muscle. So essentially your body's like playing hot potato with action potentials. Action potentials going down, going to the muscle, releasing acetylcholine. Acetylcholine is causing another action potential on the muscle. And what happens, this action potential that just got caused onto the muscle diffuses into the muscle. So the whole point of this is trying to get the action potential inside the middle of the muscle, because the middle of the muscle is where all the muscle contraction and whatnot works. And we didn't really go over the anatomy of the muscle, but the muscle has many different layers to get into the surface or get to the sarcomere. You want to get to the sarcomere. So this action potential has a few layers of muscle to go through in order to get to the middle of the muscle. And this whole thing is called the neuromuscular junction, just the separation of the synapse and the muscle. So you have this action potential, send acetylcholine. Acetylcholine crosses the neuromuscular junction to get to the muscle, and then acetylcholine causes another action potential to go inside into the middle of the muscle. Now the action potential travels into the muscle, and I'll have a more detailed diagram after this, but the action potential essentially travels to the middle of the muscle, goes down, and its destination is something called the sarcoplasmic reticulum. Sarcoplasmic reticulum is just a fancy name for the cytosol of a cell. If you remember from glycolysis, it happens in the cytosol of the cell, the outer layer. Well, the sarcoplasmic reticulum is just a highly specialized, well, it's not really a cytosol, but if you remember from cell organelles, you have the endoplasmic reticulum, which makes proteins. The sarcoplasmic reticulum is a highly specialized endoplasmic reticulum. That's all you really need to know about it. So, and that's where the action potential is going, into the middle of the cell to get to the sarcoplasmic reticulum. And in the next step, it releases calcium on certain things that we'll talk about. So, another detailed diagram I drew. So this is more detailed. You have this nerve, or this action potential going over here, causing acetylcholine to get released into the neuromuscular junction, which is right here, and then it gets released into the muscle. And now these are the sarcomeres right here. Now this is the whole muscle with the sarcoplasmic reticulum, all that stuff. But essentially the impulse to get to the muscle, it has to go through this area. So it goes down this, it travels down the sarcoplasmic reticulum, or gets there, and its destination is the sarcoplasmic reticulum, but in the sarcoplasmic reticulum is a structure called T-tubules. T-tubules. And these are pretty important. This little line, this is a T-tubule. So that's a T-tubule. There's that one over here to show it. This whole yellow thing is the sarcoplasmic reticulum. It's like pretty much surrounds the muscle. And this is a T-tubule going down it. Okay. Yep, it's right there. So going down the T-tubule, and on either side of the T-tubule, actually I'm not going to draw a structure of what it looks like, but maybe I will. T-tubule looks like this. You have this, and you don't see it on here, but it also has two sacs on the side of it called terminal cysteria. Terminal cysteria. Now this whole structure of a T-tubule and terminal cysteria is called a triad. Again, don't memorize these definitions unless she talks about them, but just go into detail in case she does. But the action potential goes down the T-tubule, and when it gets to the T-tubule, it spreads to the terminal cysterias, which you can't see in here, but when it spreads to the terminal cysterias, then the action potential, which was caused by acetylcholine's action potential, which is very strong, it's pretty much electricity. It tells the body to do things. And when it gets to these two terminal cysteria sacs, the action potential tells the terminal cysteria to release calcium. Calcium. So all this calcium gets released. Now I know this says calcium gets released from the sarcoplasmic reticulum, but the terminal cysteria is in the sarcoplasmic reticulum, so just, it's specifically, technically, the terminal cysteria is releasing the calcium. So you have all this calcium being released from the terminal cysteria. It's good and all. Now what calcium does is, calcium from a previous video when we talked about muscle contraction, we'll erase this video, we have troponin. Troponin pretty much looks like this. It's a globular protein. And a muscle contraction is essentially myosin. Zooming in a lot, myosin looks like this. It's the myosin protein, because remember muscle contraction is like a, I don't know what the word to say, but essentially all these fibers are on top of each other. So the myosin of one fiber attaches to the actin of another fiber and essentially pulls it, which is a muscle contraction. It pulls it, makes it smaller and whatnot. In order for myosin to bind to actin, because you have these myosin binding sites, but at rest, because when you're resting, you don't want your muscles contracting. You're not contracting your muscles when you're sleeping. So what happens is you have this another protein, it's a regulatory protein, surrounding myosin, or surrounding actin, so myosin can't bind to it when you're resting. So this thing is called tropomyosin, like we went over. So tropomyosin is a protein that's usually covering actin, blocking these sites so myosin can't bind it at rest. But what happens when you release calcium, calcium binds to the troponin. Well, troponin is a protein that's on top of tropomyosin. It gets pretty confusing. So calcium binds to troponin. Troponin tells the body to, or tells tropomyosin to get the hell out of the way. So tropomyosin moves. And when tropomyosin moves, myosin can bind to actin and cause a muscle contraction. And what it does is, that's when it pulls, it's called the sliding filament theory. You'll end up loving this word. Sliding filament theory. What happens is myosin pulls actin towards the other actin. So on the Z disc, different bands are like, I band looks like it's decreasing in length because it's essentially being pulled together. It's still the same size, but it's being pulled together. The H zone disappears because sliding covers it. Everything happens. So essentially calcium causes muscle contraction, because if you didn't have calcium, you can't bind to troponin, you can't move tropomyosin. If you can't remove tropomyosin, myosin can't bind to cause muscle contraction. So muscle contraction essentially, and then once calcium leaves, once calcium concentration decreases, which that happens when you want to stop exercising, essentially stop moving, but once that happens, calcium concentration is gone, you stop exercising, you stop contracting your muscles. That's why when you get to the second test, so if you heard anything in the exercise class where like calcium increases the contractility of muscles, or that's one reason why calcium is much more important than just making bone strength, whatever. That's actually a very, I want to say it's an insignificant job at calcium, but other things cause bone strength and structure like phosphorus and whatnot. But calcium mainly is involved in muscle contraction, because nothing else can cause muscles to contract or remove this troponin except calcium. So calcium is the main thing that causes it. More calcium equals more contraction or greater contractions. So to review very fast, or this one's better, you have this action potential traveling down the motor neuron. It causes acetylcholine to be released from the axon terminal, crosses the synapse, which is that space. Acetylcholine causes another action potential on the muscle to travel down the sarcoplasmic reticulum to get to the go down the T-tubule to get to the terminal cysterias. The terminal cysterias release the calcium. Calcium gets released, binds to troponin. Troponin removes tropomyosin, all that good stuff. And when you want to stop exercising, the calcium goes back into the terminal cysterias. So the terminal posterior is like the sac holding it. So we went over sarcoplasmic reticulum, what it was. Sarcoplasmic reticulum is great if for type 2 muscle fibers or fast twitch muscle fibers, they have a more defined sarcoplasmic reticulum. That means because fast twitch muscle fibers contract faster. So if you have a more defined sarcoplasmic reticulum, this whole process is more efficient of contracting the muscle. And eventually, we didn't talk about how ATP is involved in this, but when we get to the cross bridges, which we'll talk about now actually, cross bridges, or when actin binds to myosin, when myosin binds to actin, when you have this globular protein, you have myosin, calcium, we bind to troponin, we move the tropomyosin. Now, where ATP plays a role in this, all this ATP we made from glycolysis, from beta oxidation, whatever. Nothing is possible without ATP, and ATP, this is where ATP comes into action. In order for myosin to bind to actin, it needs ATP. ATP is floating in the muscle cell, all this ATP that you just made, and it binds to actin, or binds to the myosin. It makes it active, essentially. Myosin is just inactive until ATP binds to it. ATP binds to it, it activates myosin, and when this happens, this ATP splits to ADP and phosphate. Because that splitting of that third phosphate is what causes this massive release of energy. And it splits, it activates myosin. Myosin binds to actin now. And when it binds to actin, it essentially holds on to actin, and it forms a bond called actomyosin. Just put the words together. And that's called a cross bridge. So it binds to actin, forms a strong-ass linkage called actomyosin, and nothing can really break this linkage. But when muscles contract, obviously you need to break the linkage and pull another actin towards it. Again, go to YouTube, just type in sliding filament theory, and you can watch all this because it's much easier to see a visual of it. And in order to release myosin from actin, so it can bind to another actin, another ATP has to come and bind to it in order to release it. So to cause the muscle to stop contracting. So another ATP binds and splits. So essentially it takes one ATP to activate myosin, one ATP to detach the myosin. So an example of this is something called rigor mortis. When someone first dies, or even a Charlie horse, because you haven't really experienced dying and have your muscles stay and contract, but a Charlie horse essentially this is what a Charlie horse is. A Charlie horse is a muscle that contracts and it doesn't decontract, I guess, or it doesn't release that bond because you're dehydrated or you don't have enough electrolytes, you don't have enough ATP in your system. So what happens is myosin binds to actin, pulls it, it causes the muscle to contract, and you don't have enough ATP to release that bond. That's why, how extremely painful it is and whatnot, if you feel your muscle, you can feel the muscle contract, and you can feel the muscle, it's contracted, it's not decontracting, and it's just like quivering because it's contracted. So it's very, very painful. Nothing can break that bond, essentially, unless obviously you drink water or you massage it. So it's very painful when this bond's held. And when someone first dies, if they die in a muscle contraction, when they're tensing the muscles, if they die, the muscle doesn't decontract. The muscle's literally like rigid because these ATP bonds did not break. So that's everything you need to know about muscle contraction, I believe. Yeah, it's pretty much everything you need to know. And now the very last video, I'll just go over some actually I'll cover some really quick things in this so I don't have to make a new video, another whole video. But essentially, let's see what other questions we have. What is the relationship between fiber type distribution and performance? We already went over this. Slow twitch muscle fibers, a long distance runner will probably have more slow twitch fibers. Or long distance runner, really an endurance athlete will have more slow twitch muscle fibers. Long distance runner, because slow twitch muscle fibers are fatigue resistant. They can create a lot of energy. So an endurance athlete will have more slow twitch fibers. Now, strength athlete, well, not really strength athlete. Strength athletes have like 50-50 to the weightlifters because you really don't have a preference to slow twitch or fast twitch. But like sprinters, high jumpers, gymnasts, they have more fast twitch muscle fibers because, well, their activities involve more fast twitch fibers. They need energy much faster. So that's pretty much fiber type distribution. So if you're a long distance runner, most likely you have more slow twitch muscle fibers. One section was on training adaptations. Well, with training, obviously exercise gets easier. What happens physiologically, one thing that happens is your body gets better at storing glycogen or storing blood glucose. If you can store more glycogen in your body, you have more glucose on reserve. If you have more glucose on reserve, you can last longer. Just like you have a bigger bank account, you have more money, you can last longer with more money. Very similar. I swear I'm not obsessed with money, just everything works perfect relating to that. Okay, so this is pretty much the last video, the second to last video. The last video will be just going over questions that I thought Moffat would ask, or I think she'll ask based on everything that we went over.